Hello and welcome to this lecture. We're going to see the most important application of derivatives and mean value theorem, and that is Taylor's theorem. Okay, so Taylor's theorem is a really wonderful and beautiful result, which gives you, which gives you ability to predict a function based on the value and its derivative at one point, derivatives, higher order derivatives at one point. It's a very powerful theorem. It gives, it has tremendous applications across engineering, across science, in various places, and it's also a very fundamental intuitive way in which you think about a general function which is well behaved and smooth. Okay, so Taylor's theorem is very important. Once again, you will see derivatives and mean value theorem in particular will play a very important role. So a couple of things I want to tell you about Taylor's theorem before we start. It's a bit of a long lecture. It's going to be a couple of lectures in which we'll cover, and then we'll do some problems on Taylor's theorem at the end. But I want to impress upon you, so I will do some proofs. The proofs are not too critical, but you have to understand the result. Okay, so there will be a result, and then there will be an illustration of the result, and maybe even problems with the result. The results are important for you to understand. The proofs are quite simple actually, but then if you find that the proofs are a little bit confusing, you can come back and look at the proofs later on. They are not so important as far as this course is concerned, but for math in general, these proofs are very important. And once again, we'll use the same technique we've used throughout this course. We'll start with simple, easy cases, right? We'll build the theory for that simple case, and then we'll slowly complicate it over and over again. Okay, so just stay with me. You'll see that the ideas are very simple and elegant, and finally we get a powerful result. Okay, so let's get started. Okay, so what's the basic idea behind Taylor's theorem? The basic idea is the following. Okay, so this says constant approximation. I'll come to it, but the basic idea is you have some function which you know is smooth in the sense it is continuous, it is differentiable, multiple higher derivatives exist. So it's a very sort of smooth function, and you know its value at a, and you know which is f of a. Okay, at some x equal to a, it is f of a. Okay, and then you have an x which is near a, and you're wondering what x comma f of x could be. Where could it be? Can I approximate just based on this? Okay, so maybe I know more about this point f of a. Maybe I know the derivative at a. Okay, maybe then maybe I can say more. But in case I don't know even the derivatives, I only know f of a. Then what will you say is x when f of x when x is near a? What can be the best approximation? What is the best you can do if you don't know derivative, if you don't know anything else? One thing to do is to say it's constant, right? So you can say f sort of is equal to f of a somewhere near a, so that you can say a constant value, right? So f of x is approximately f of a, isn't it? So it seems reasonable. It's the best you can do if you don't know anything else. But then how good is this approximation? Okay, that's the question, isn't it? And that question can be answered in a wonderful way using mean value theorem and derivative. Okay, so it turns out how good is this approximation depends really on how the derivative behaves between a and x. Okay, the derivative of f prime of x, how it behaves between a and x determines how good this approximation is. And that's sort of intuitive, right? So derivative somehow captures the rate of change between a and x, and if the rate of change is very small, then your constant approximation is also going to be small. If the rate of change is very large, your constant approximation is going to be bad because it's changing wildly, and then you're making a constant approximation when it is changing a lot. Okay, so this is the core idea here. We're going to use mean value theorem to relate the error in this approximation to the derivative between a and x. Okay, so here is how we'll do it. Just watch how this works. It's very clean. Okay, so we're going to assume f is differentiable in ax. Okay, so of course the derivative has to exist there, otherwise we have no business doing it. By mean value theorem, there is a c in ax, okay, such that what? We know this, f prime of c equals f of x minus f of a by x minus a. Okay, so this we knew before from mean value theorem. I'm going to rewrite this a little bit. I'm going to rewrite this, and I get f of x minus f of a equals f prime of c times x minus a. Okay, so notice this f of x minus f of a which shows up here, right? You see that here, right? Now that is my error, isn't it? Error of constant approximation. And notice what it depends on the other side. It depends on how far away from a you are. Okay, if x goes farther and farther away from a, this quantity also tends to increase. Another very crucial quantity is the derivative, and the derivative at some point c, right, between a and x, that is f prime of c. I don't know its value, but it depends on that. If the derivative is very large, then you expect this to go large. Okay, so this is a very interesting another way in which to view this. Instead of saying, I know f of x, how do I guarantee, I mean, what can I say about the derivative? It's the other way around. I know the derivative, maybe, I know how far I am, can I say something about f of x? Okay, so it's just turning the question around a little bit. Okay, we studied mean value theorem as, I know f of a, I know f of x, what can I say about the derivative between a and x? Right? So we started, but here we are turning it around. We are saying, I know f prime of c, I know f of a, what can I say about f of x? Okay, so it turns out if I end up with a constant approximation, then this error depends on this derivative. Okay, so if you want to make it more precise, this is how you can make it more precise. You can take absolute value. So absolute value of f of x minus f of a equals absolute value of f prime of a times absolute value of x minus a. Why am I taking absolute value? Because positive and negative is a bit confusing. So I just need the magnitude of the error, right? So that's okay. So this gives you a very clean idea. And then what do I do with the c? The c is a bit confusing. I know it's some point between a and x. How do I get rid of the c? This is a clean little idea that you can use. You can say, I don't know what c is, but then f prime of c will be smaller than its maximum value, the maximum value of the derivative in the interval a comma x. So I'll simply upper bound f prime of c, absolute value, by maximum of over a comma x, absolute value of f prime of u. Okay, so this precise result relates the error of constant approximation to the value of the derivative in the interval a comma x, which is the largest rate of change in a comma x, multiplied by how much you move away from a. Okay, mod x minus a. Okay, notice once again it's a very elegant result. It says the highest rate of change between a and x multiplied by the width of the change mod x minus a is an upper bound to the error between f of x and f of a. And this result is facilitated by the mean value theorem. Okay, for any function f, as long as it's differentiable, this is going to be true. Wonderful result, isn't it? So this tells you how to approximate f of x with when around a, when you don't know anything else, and the error is also pretty good if the rate of change is small. Okay, of course this is not the only thing we can do, isn't it? If we know more about the function f at a, we can do better and better approximations. Of course, we know linear and quadratic approximations. We've seen this over and over again earlier. So here in this case, I know at a that f takes value f of a. Maybe I also know that maybe I also know the derivative at a and the double derivative at a. Okay, now I know more information. So when I have more information about the function f at a, I can do better approximations for f of x. Okay, how do I do this? For instance, linear approximation, we've seen this quite a bit. There is this linear function L of x, which is f of a plus f prime of a times x minus a, which this I expect to be close to f of x, right? And you can see very interestingly, we've seen this before also, this function L matches with f at a, and also the derivative of L matches with the derivative of f at a. Okay, so it's a linear function, but it matches with, so L of a equals f of a, and L prime of a is also equal to f prime of a. Beyond that I can't say much, right? So I don't know, the derivatives may not match, because L double prime of a and all is 0, right? But on the other hand, f double prime may not be 0. Okay, so I don't know what happens to it beyond it, but at least these two values are equal. Okay, so this is one approximation. Yeah, I expect this to be better than the constant approximation. Now once again the question is, how much better? Can we quantify it? How do we use mean value theorem? We don't know yet. Okay, better still, even if you can use the f double prime, you can get the quadratic approximation. We've seen this before as well, right? You can do f of a plus f prime of a times x minus a plus f double prime of a by 2 times x minus a whole square. You remember why this 2 comes and all, right? I'm trying to equate between q and f, the value at a, the value of the derivative at a, and the value of the double derivative at a. If you do this, you will get this approximation. So these two, I believe, are better approximation than the constant approximation. But then, can I bound the error? Okay, how do you use mean value theorem to bound these errors, the error between f of x and L of x, f of x minus q of x? If I can do it, if I can understand it, then I can approximate, then I can predict, right? Based on what I know at a about the function f, its derivative, double derivative, I can predict what could possibly happen to the function somewhere a little bit away from a, which is not too far away, and the derivatives and all are small, right? So how do we do it better and better? We need to improve our mean value theorem, make it a little bit better. Okay, so what I'm going to do in this lecture is to show you how we do it for the linear case. Okay, and once again we're going to do simple, right? For the constant case we were able to do it with mean value theorem. How do you do it for the linear case? We'll do it step by step, and then we'll go to quadratic, and then we'll go to cubic, power 4, power 5, right? Any power, right? That will be the end of Taylor's theorem. So let's now jump into the linear approximation. Okay, so you remember mean value theorem. First we proved something called Rolle's theorem, right? Once we proved Rolle's theorem, we were able to quickly use it and do this clever little modified function which gave you mean value theorem. We're going to do the same thing again. Like I said, the same tricks get used over and over again in slightly more and more complicated fashion. All of math is like that. Okay, so I need a little bit of notation just to make sure that I don't have to keep repeating this over and over again. This is very common notation called Ck of a comma b. What is Ck of a comma b? It means that f is differentiable k times. Okay, f is differentiable k times, as an fk exists in AB. Okay, what is k? K could be k is some integer, 1 for instance, or 0 for instance, 1, 2, 3, so on. So if suppose k is 2, then it means that f is first of all continuous, and then f prime exists, f double prime exists, and then f double prime is also continuous. Okay, so that's what this means, right? So if k is 2, f prime exists, f double prime exists, f double prime is continuous. Okay, so that's the notation Ck. I will use it a little bit so that I don't have to keep repeating this over and over again. Okay, so here is my generalized Rolle's theorem for f double prime. Okay, we have a Rolle's theorem for f prime, right, which is f of a equals f of b, right? This is how Rolle's theorem works. No, f of a equals f of b. There is a point C such that f prime of C is 0, somewhere in the middle. That's Rolle's theorem. Now, in the generalized Rolle's theorem for f double prime, we are going to say there is an f of b equals f of a, and f prime of a is 0. Okay, f prime of a is 0. So notice I'm drawing the curve sort of like that. So the slope here is 0. Okay, so this is an additional condition I'm going to assume here. Okay, this is an important condition. In Rolle's theorem for f prime, we only use this condition, right? We only use f of b equals f of a, right? We don't have this guy. This f prime of a is 0 is a new condition I have in this case. Okay, why? Because I want to go to f double prime. Okay, so notice the conditions here. This basically says f is differentiable once and the derivative is continuous. So it makes sense for me to say f double prime exists in AB. Okay, f double prime itself may not be continuous. I'm not asking for that, but f double prime exists in AB. It could be continuous. I mean, we are generally dealing with smooth functions here, so it's no problem. So what happens if these 2 points are true? Okay, f of b equals f of a, just like before, and f prime of a is 0. F prime of a is 0. Then it turns out there is a point x2 in AB such that f double prime of x2 equals 0. Okay, so notice how this additional condition is required here, and then but I get this additional guarantee. I get f double prime of x2 is 0. So let me just illustrate this for you. Okay, and along with the illustration we'll do the proof also. Okay, so you have f of a equals f of b. This I know for sure. So by the regular Rolle's theorem, we know that there exists an x1 in AB such that f prime of x1 is 0, right? So we know this we always knew. Now additionally, we know that f prime of a equals f prime of x1. Okay, so that's the trick here. Okay, so this first derivatives are equal at a and x1. Okay, of course they are both equal to 0. That's why I wanted the f prime of a also to be equal to 0 here. That's why this condition is required here. Okay, so I know that if f of a is f of b, I will have an x1 such that f prime of x1 is 0. Okay, so this is Rolle's theorem. We used to call it C before. I'm calling it x1 now because I'm going to use it over and over again. So you'll see this will be important. So magically, because of this condition, I know that f prime of a equals f prime of x1. These slopes are the same. Okay, now what can I do? Whatever I did once, I can do it again, no? F prime is a function. It's equal at a and x1. So what will Rolle's theorem tell me? Rolle's theorem says there is an x2 in a comma x1 such that f double prime of x2 equals 0. What is f double prime? This is just the derivative of f prime. This is the exact same result as this. Do you see that? Okay, so this is a wonderful way in which we use these basic deductions over and over again. You repeat the same thing. you get wonderful new results. Okay, so I hope you see this method here. It looks a little complicated, but you can see I'm repeatedly using the same result, and I've added whatever condition I need here to enable that to happen. Is that okay? Hopefully you see this result. So now we have a Rolle's theorem for f double prime. Okay, so it needs this additional condition, f prime of a is 0, then you are guaranteed that in AB there is a point, of course, where f prime is 0. There's also a point where f double prime is 0. Okay, wonderful, isn't it? Right. So now we're going to use this to get a slightly more complicated mean value theorem, which is useful for linear approximations, for bounding the error of linear approximations. So how do we do this? Here is Taylor's theorem. I'm going to call it Taylor's theorem. It's a form of Taylor's theorem, but this is a version which is useful only for linear approximations. We'll do more complicated versions as we go along, but this one is useful for linear approximation. So what is Taylor's theorem for linear approximation? Okay, so f is see, these conditions are just smoothness conditions. It's the differentiable, derivative is continuous, f double prime exists in a comma x. Okay, so then there is a point x2 in ax such that f of x equals f of a plus f prime of a times x minus a plus f double prime of x2 by 2 times x minus a whole square. Okay, so this is sort of like mean value theorem. You might say, why am I calling it mean value theorem? So let me just write this out. What is mean value theorem? So you have a comma f of a and then b comma f of b. Mean value theorem, I'll abbreviate it as MVP. It says there is a point C such that f of b minus f of a by b minus a. Okay, so this is derivative. What about double derivative? Okay, so this is what mean value theorem now says. What is Taylor's theorem saying? For degree 2, there is a point x2, right, between a, b, there is a point x2 such that f double prime of x2 is slightly more complicated, right, f of b minus f of a times b minus a divided by b minus a whole squared by 2. Okay, so this is just, I've rewritten this guy. Okay, I've pushed this to this side, f of x minus, okay, maybe I didn't write it carefully. No, I think, yeah, this, sorry, f of b minus f of a minus f prime of a times b minus a divided by b minus a whole square. So I'm just rewriting this guy. I'm pushing this a to this side, this term also to this side. I'm dividing this x minus a whole square by 2. Instead of x, I've used b, okay, in that other illustration. So what this tells me, so this Taylor's theorem is also like a mean value theorem, like MVT for f double prime, isn't it? Okay, so mean value theorem just tells me the first derivative has to satisfy this condition. There has to be a C for which the first derivative is this guy. What this Taylor's theorem is telling me now for f double prime is there has to be an x2 here somewhere, right? C is somewhere here, x2 is also somewhere here, right? So there has to be an x2 here such that f double prime of x2 is f of b minus f of a minus f prime of a times b minus a divided by b minus a whole squared by 2. Slightly more complicated, but the spirit of the result is the same. Okay, so I'm able to say something about f double prime. So instead of writing it like this, which will be uglier and uglier, we think of this in a different way. Okay, so that is where the nature of this result comes in. The nature of this result is a little bit different, right? So I know something about f at a, I know its value, I know its derivative. I've gone to this point x, which is a little bit away. Okay, right? Look at this picture here. I know a, I know f prime, I know f prime. I've gone a little bit away from a. I want to say what I know about f of x here. Taylor's theorem is in that spirit. It tells you f of x actually at point x can be written in this fashion. Okay, so now this f of a plus f prime of a times x minus a plus f double prime of x2. Now this x2 will depend on x. Okay, keep that in mind. If you vary x, this f double prime will vary. This x2 will vary. Okay, so this x2 is a point that depends on x. As you change x, this f double prime of x2 changes. Nevertheless, there can be a quadratic expression like this to which you can fit an f of x. Okay, so this is like a very, very nice and clear result on what what you can say about f of x in this fashion. Okay, so here is a little bit more of an explanation. A comma f of a, in terms of the error of the linear approximation, right? That's also is important. From a comma f of a, if you know the derivative, my best bet is to do a linear approximation for the function. This is the linear approximation, the straight line f of a plus f prime of a times x minus a. And then this will have an error, right? This is f of x here, and that is L of x. This the green color guy is L of x, red color guy is f of x, and the error is absolute value f of x minus L of x. Okay. So of course, it can also be below, the line can also be below, so it can be negative. So we'll look at the absolute value. So this result, this Taylor's theorem, gives me a way of bounding f of x minus L of x. Okay, why? Because this guy is L of x, right? This guy is L of x, and this is f of x. And Taylor's theorem tells me f of x minus L of x has to satisfy this condition. Okay, that's where I'm getting here. Okay, so f of x minus L of x, because of this wonderful form for this, gives me some condition like this guy, right? There is an x2 such that f of x minus L of x is equal to f double prime of x2 by 2 times x minus a whole squared. I don't know what this x2 is. This x2 is going to keep depending on x. So what I'm going to do is, I'm going to simply max over u in ax f double prime of u by 2. So I'll get an upper bound on this error. Okay, but notice magically I now get a absolute value of x minus a whole squared. Okay, of course, for the square you don't need absolute value, but anyway, you can put it out there. It's absolute value of x minus a whole squared times max u in a comma x f double prime of u by 2. Okay, I want you to think about how this is similar to the constant approximation. Let me go back to that slide. We come back here. So notice we got this relationship, right? F of x minus f of a is controlled in this fashion. We are now able to say how good the linear approximation is, not just the constant approximation. We generalized the Rolle's theorem, and we now generalized the mean value theorem, so to speak, and put it in a different form, which is called Taylor's theorem, and we're able to bound the error in linear approximation. The maximum error, the error in linear approximation, is upper bounded by mod x minus a whole squared max of the double derivative. So if the double derivative is small, right, you've not gone too away from a, and double derivative is small, then you get an error which falls as mod x minus a whole squared. Now if x minus a is less than 1, you know that x minus a whole square is smaller than x minus a, right? So this has potential to be a better bound. Okay, so that's why linear approximation can be better than the constant approximation that we saw before. Okay, so this is the spirit of the theorem. I hope you understand this. So it's slightly more complicated than a simple mean value theorem. The best way to view it is like this. Instead of seeing it as a mean value theorem, the best way to see it is to say that I'm going to try and approximate f of x by a linear function. Okay, what is the error? The error, it turns out, is f double prime of x2 by 2 times x minus a whole square for some x2. And this x2 I may not know. So to get a good bound, what am I going to do? I'm simply going to max over u ax, absolute value of f double prime of u by 2 mod x minus a whole square. Okay, wonderful, wonderful result on the error of linear approximation. So let's conclude this part of the lecture with a quick proof of this result. It just uses the generalized Rolle's theorem. Okay, so there's nothing more to it. Same as before, we used Rolle's theorem and proved mean value theorem. We generalized Rolle's theorem. We're going to simply generalize the next step. Okay, the proof goes exactly in the same way. So I'm going to use a function g of u, which is f of u minus f of a minus f prime of u minus a. You notice here how this is exactly this guy, right? And then instead, I don't know what this is. I have to prove that this is f double prime of x2 by 2. Since I don't know, but I know this form is true, I'm going to put some s here. I don't know what that s is. I hope to show that s equals f double prime of x2 by 2 for some x2. That's what I hope. But right now, I'm going to put s here. So I get minus s into u minus a whole square. This is g of u. Now, what type of properties does this g of u satisfy for any s? No matter what s is, g of u satisfies these wonderful properties. First thing I'm going to do, okay, so let me take that back. So not for any s, g of u looks like this, but I'm going to pick a specific value for s. What is my specific value for s? I'm going to pick s such that g of x is equal to 0. This s is going to be selected so that g of x is 0. That can be done, right? I'll put u equals x. If I put u equals x, I'm going to get g of x equals f of x minus f of a minus f prime of a times x minus a minus s into x minus a whole square. Move all these guys here, solve for s. I can solve for s, no? So I can solve for x. So it's possible to pick an s such that g of x is 0. Okay, this is important. Once you pick that s, g ends up satisfying so many interesting properties. First thing is g of a is 0. You put u equals a, you get 0, right? and g of x is also 0. Why? I picked my s like that, right? My s was picked like that. Okay, I still have to show s has this form. I haven't come there yet, but I picked only s in this fashion. G of a equals g of x equals 0. Now, more interestingly, the derivative of g at a is also 0. Okay, why? Because if I do a derivative, I get f prime of u minus this f of a is a constant, it will go off. Here, if I differentiate with respect to u, only f prime of a will remain. So, these two will cancel out. And here, I will have 2 times u minus a, 2 times u minus a, and if I put u equals a, I'll get 0. Okay. So, check this. I will leave this as an exercise. Okay. I'll leave this as an exercise. This showing that g prime of a equal to 0 is an exercise. Try it. It's quite easy. You will get this proof. So, G satisfies all these conditions. Now, we can use the generalized Rolle's theorem, right? Because g of a equals g of x equals 0 and g prime of a is 0. By generalized Rolle's theorem, I know there is an x2 in ax such that g double prime of x2 is 0. But what is g double prime of x2? If I do a double derivative, all these guys will vanish. Because if I do a double derivative, these things will not share. This is a constant, this is a linear function, it will go off. But f double prime of u will stay, so that you will get g double prime of x2 is f double prime of x2. Here, this u squared is there, so you will get a minus 2 times s, okay, equals 0. So, this shows you that there is an x2 such that s equals f double prime of x2 by 2, and I am done. Okay. So, this is the proof of the linear approximation, error in linear approximation Taylor's theorem for degree for linear approximation. Okay. So, hope you see this. This is actually very similar to the way in which we did mean value theorem proof from Rolle's theorem. We have just modified it. We have gone to the next degree, and then we have used this additional choice for s very carefully. Then once we chose that, we see that this g satisfies all the conditions for generalized Rolle's theorem, and then we know that there is an x2, and we have to just differentiate, and then we have to differentiate this g of u, and we get this magical result that this s also satisfies f double prime of x2 by 2 for some x2. Okay, so that's the end of this lecture. The proof, if you didn't understand, it's okay, but you should understand the nature of this result and how this implies a bound on the error of the linear approximation. So, we're done with linear. Okay, we're done with constant approximation. Mean value theorem gave us a very simple extension of that theorem, gave us the error in the linear approximation. We're going to do a very similar extension to study quadratic and then general polynomials of higher degrees. That we'll do in the next lecture. Thank you.